Okay, so today we're now going to continue our conversation from last class, but help me out. What did we talk about last class? What did we talk about? Anyone? I blanked your name, I'm sorry. Charlie. Excellent. Okay, so linear regression and the four assumptions of regression. What's the basic idea behind linear regression? Like what are we trying to do with it?
Trying to figure out you have like a scatter plot and you're trying to find the linear regressions of the line.
Yep, the line of best fit, right. So there's going to be some relationship and we're trying to untangle essentially that slope of the line. How, if you increase one, how much will the other increase? So a couple of things to remember about linear regression. That means A, we have to make a causal claim. And that is what you do with your proposals. You make a causal claim. This one thing determines this other thing. If you change X, that means you change Y. And I think, too, is the whole point of doing this is we get some idea of the level of impact. Right? If you change X, how much does Y change, and in which direction? Okay, so as long as we're on the next few proposals, this is a reminder as well that in about a week, it's a week, your tables are due. So the tables involve three things: your regression analysis, your summary statistics, and your correlation table. Now I'll talk about why you need a correlation table next class, but the summary statistics is going to be straightforward enough. Mean, median, mean and median, maximum, minimum, standard deviation. I think are the ones I require. I have a full list on the assignment page. Your regression analysis, I'll show you how to do that today. You've done a simple one. We're going to be doing a multivariable one because you're going to need multivariable because you have three different things affecting this other variable. And of course, a correlation table. All right, so let me show you an example. This is data set 6 from my website to show you what these sort of analysis do, what these multivariate analysis do. And I cannot, for the life of me, remember exactly where I got this information from. So I apologize for that. Usually I like to be able to track exactly where I get my data from. I believe this is real data because I wouldn't have recorded it otherwise, or wouldn't have found it and saved it somewhere otherwise. I just can't remember exactly where this is, but it's housing data. So here we have the price of the house in dollars, US dollars. Here we have the year the house was built. Here we have the square feet of the house. This is a big house, 3,600, almost 3,700 square feet. Wow. Here we have how far away it is from the city center. And here, how long it's been on the market. And this makes me think, too, this is from like 2010 or something, because 900 days on the market is a long time to be on the market. Just give up. It's like 2.5 years. What are you doing? So, cut your price. How's your price expensive? These are all sold houses, too. These are offers. So this house was on the market for 900 days before someone finally sold it. Before someone finally bought it, I mean. Okay, what do you think the relationship is between miles from city center and price? Michael? Well, it makes sense. Why?
There's usually more in the city, like shops and
walkability is really nice. There's also another really big reason too, something that people do almost every day. Work commute, exactly. Your commute According to some of the data I've seen, is like for most people the least pleasant part of their day. So being able to cut that down is a really valuable thing. So a lot of people are willing to pay premium to cut it down. A lot of people work in the city. This, by the way, interesting enough, and this has come up in some of the analyses that people have done. You note in the state level data, DC is always like a weird one. Like its average income is way high, for example. The reason why is because DC is an odd observation. Unlike the states, which the state would include a city and then the surrounding suburb area, DC is largely just the city. I mean, there's some suburban parts of DC, but it's largely just the city. And so when people commute into DC, they're adding to its total income earned because that's where they earned the income. But because they don't live in DC, they're not contributing to the population. And so as a result, the average income for DC is like really high. And that's a bit of a deceptive. So you can, if you do your analysis, you can make an argument that if you're including that, you should exclude DC as an observation. It's just weird. It's just weird. But it's a judgment call to include it or not, because some people get pissed off, understandably, that you start opening the floodgates of saying, I'm just going to eliminate observations that I think are weird, because that's a term with a lot of give to it. People can manipulate the data set by removing the weird observations that aren't really that weird. Okay, so then let's run a regression, because maybe I'm curious as to, if I get closer to the city, how much more I can expect for paid for price. Maybe I'm a developer and I want to build a new housing structure, and I want to get some idea on how much I should charge to see if it's worth my while, to see some idea on my budget, to be able to plan ahead. Or maybe I am a house flipper, people who find houses that are in really bad shape and turn them into something really amazing and then make money off of that flip. So I need to figure out what would be a good candidate to be flipped. So I need some idea on some base level of money I could expect to earn. So I want to run a regression then. I want to be able to predict the housing prices with miles from city center predicting price. Obviously, it can't go the other way if you change prices and change location. But if you change location, that should change price. How do I do that? How do I run a regression? Options, that is, go, and put the analysis back. I already have it active from the last class. Hit OK, and you should all have the analysis.
Data set 6, right?
Yep, data set 6. Okay.
Are we supposed to highlight it?
You don't even have one. It's just selected.
No, just
You want to go into the housing data tab, just because it defaults to the country data tab. Get that, open it up. Okay. Now what do we do? I have it here. Yeah. Oh, just the first one's fine. Yeah. Next, select the box so it's a text file. Yeah, great. Well, what do we need if we want to run a regression? Regression. So let's select regression down there. And you should get, of course, this friend that we've seen before. Okay. So I want to select miles, I'm going to select negative ones, I don't think I can do that. And how do I want to set this up? How should I set this up? Exactly, so D1 to D101 for the X, and for the Y, A101, or A1 to A101. So of course A is first, but then put Y first, and then X is second. D1 to D101. Oh, and we need a base to put it out, so we'll just put in output range, and I don't know, we'll select G1, sure, let's start there. Okay. We good? All right. Let's hit okay. So this is the area that we know. Talk about the other parts of the bed. This is the area we know. What do you notice about this? Michael, what do you notice about this? What is it? Okay, what's the coefficient for miles from the city center? Wait, say again, what's the coefficient for miles from the city center? Oh, I see. Okay, I have a little mind of 5518. Yeah. So that makes sense, right? Why does that make sense? Michael? I'm sorry, Adam, you have a point?
Because when the miles of the city gets smaller, the price gets lower.
As it gets closer, or as that number drops, the value should increase. And as you get farther away, or as the miles from the city center increases, the price should fall. Right. So for every mile that we get away from the city center, the price falls by about $5,500. Are we good so far on the same page? But there's a problem. What's the problem? CJ? We'll get to that in a moment. This is a different problem, but just on the space analysis. What's the p-value? What was that? So what does that mean? 0.06, what does that mean? Oh, sorry, it's not 0.06, it's 0.6, right? What does that mean? What does that mean? It is not statistically significant. That's absolutely right. What do you mean, Adam?
But the critical p-values we know by heart are less than efficiency plot, and then like 1.7 or something.
The critical p-values you do know by heart, because the critical p-values are the alpha values. So for 95%, the 0.05, and for 99%, 0.01, and for 99.9%, 0.001. Because the p-values have to be smaller than those critical alpha values, so you get statistical significance. Remember, for p-values, the smaller the value, the higher the level of statistical significance. For t-values, the larger the absolute value of it is, the greater the threshold of statistical significance. Our t-stat is tiny, not even greater than 1. It's not even greater than 0.5. Take the absolute value. Our p-value is huge. Remember, it maxes out at 1. It's 0.6. To even get a base level 95% confidence, it's got to be less than 0.05. It's more than 10 times that. So we do not have statistical significance. We are claiming something really strange. We are saying that as a house gets farther from the city, the price doesn't change, because we cannot reject our null hypothesis. We have to fail to reject our null hypothesis. And our null hypothesis would be beta is 0. Doesn't matter. Right? Location doesn't matter. Like color shouldn't matter. Or. Are we good so far?
So the p-value is just an alpha you're saying. So
p-value is compared to alpha.
Okay, so we're saying like 63, we're saying it's like 30, it's having 37%.
Yeah. It's like significant of 37, yeah. So that's really shitty, right? It's really terrible. Any other questions? So, how is this possible? Because all reasonable intuition tells us that this should matter, that location matters. That's like all of that. That's the three most important things about real estate, right? Location, location, location. And here I'm giving you data that's like, no, it doesn't. It doesn't matter. And so this is strange, right? Everyone agrees it's strange? What's going on? How would you compare houses near the city, say downtown DC, versus houses way out? How would you compare those houses? Square feet, what do you mean?
In downtown, I guess it's more compact, so houses are smaller, more the suburbs, is more land.
You got office space, right? Houses are large. So, which houses should go for more money? Small houses or large houses? Large houses, clearly large houses. So this is so now you see a bit of the puzzle. We are comparing houses that are close to the city and small with houses that are far from the city and large. And it's not clear which one should go for more money. The one that's far from the city and large, that's a good reason not to go for a lot of money. As you get closer to the city, they get smaller and smaller. So on one hand, they're getting better because they're getting closer. On the other hand, they're getting worse because they're smaller. And so it's not really clear. What we want to do is we want to be able to take that same house of the same size and move it without changing the size and see how prices change. As CJ points out, we need to include square feet. And luckily we have that. So rather than doing this equation, y hat I equals beta 0 plus beta 1 x1I, we are going to do this equation. We're now just adding a second independent variable. You, for your papers, will have 3 independent variables. But as you see, it's easy just to add another independent variable on. It gets a little annoying for logistic purposes, but it's not bad at all. So let's do this again. Regression analysis. But rather than only focusing on miles from city center, let's also throw in square foot, which is column C. Oh, and I want to change where I put in the output, right? So I want to be able to do that output later. So I'm going to override this yet. I'll put a G20. How did you get back to that screen? Oh, I just hit data analysis regression again. And it remembers what you did last time. Is that what everyone did? Make sure you get a new place for your output. Oh, so rather than highlighting just one column, I'm highlighting 2. I'm essentially already from. So the way that this part works is you make a box. The first number is the upper left-hand cell. In this case, it's C1. And the second number is the lower right-hand cell, in which case it's D101. And that makes 2 variables. Make sure, by the way, that you include 1, and also make sure that you include the labels. Because you want to be able to distinguish one variable from another. So, okay. What did you say now? That's better, right? That makes more sense. Is miles statistically significant? Is miles, here's square feet? Yes. And again, I appreciate the fact because we include labels, we know which one's which. How do you know this is significant? Exactly. Our p-value is pretty low. It's not super low. What level of statistical significance is it significant at?
A little bit above 98.
Yeah. I don't know how you do that. You're 98.5%. Right, because you didn't have to stick with it. But typically, though, we would say, well, it's statistically significant at 95. It's not a 99. But you're right, it is significant at 98.5. And note, too, what happened to the coefficient. It's huge, right? It's got a lot better. Before it was 5,500. Now it's almost 24,000. Because it can untangle a lot of the countervening effects from the square feet, right? It can say, oh, okay, holding that square feet constant, I can look at this data. Is square feet statistically significant?
Yes.
Yes. How do you know? Exactly. Again, the p-value is really small. This is not 4.8, as people keep wanting to do. This is point, and then there's 10 zeros, and then there's 4.8. So it is very, very small. In practice, by the way, you would round. So when you do your table, when you do your regression tables, so when you do any of your tables for the upcoming assignment, don't include include as many decimals as you can fit in. That's disgusting and awkward. Don't do that. You don't need 8 decimals to demonstrate something. You need at most 4. So I would put in, if I were to put a table of this, I would do that for square feet. 0.000 for the p-value. I do that because no one will think it's literally 0. Anyone who knows what they're talking about and can read the table and knows what this means knows it's not literally 0. They just know it's really, really, really small. You don't need anything beyond those 4 places. So don't, for your correlation table, I see this all the time, where you're like, oh, the correlation table is negative 0.54631959867. I don't really need all that crap. I need it to here almost. 4 is pretty standard. Preferably you do 3 for the correlation table, so that's a big deal. But it's the same story for your summary statistics as well. Make it reasonable. 4 is absolute max. Sometimes you should even go 4.
We wouldn't change this, right?
Well, yeah, because that's something that Excel does. But you have to take this and make it look presentable, because you also don't need all this information too. You don't need the standard error or this stuff over here. And that's why I give you that sample, the sample tables. You can take a look and see what I did to give you an idea. Anisha, do you have a question?
Yeah.
Oh. Good analysis. You notice that my X range is hard because you're way in the back. But my X range is not D1 to D101. It is C1 to D101. And so as a result, I'm now doing I'm doing both columns here. You're giving me this look like you don't believe me, or you're not sure what I'm talking about.
So this will be for your X range that's
Mm-hmm. And so, this C1 to D101. That will give you 2 variables. Right? Now you're covering 2 columns. Yep. Any other questions?
And what are the directions for this thing that you're talking about?
It's on leftward. Under all the regression tables, I think it's okay. Any other questions? All right. Now let's switch over to country data. That's another one. Let me simulate something that you might do for your paper and show you something that Excel has issue with. Excel is really powerful, but Excel is not built to run regressions. Right. There are specialized programs like Stata and Minitab that run regressions really efficiently. Excel doesn't do it very efficiently. And so as a result, there's some quirks you have to deal with in order to run it. Excel's nice because everyone has it, but Excel's limited. I want to run a regression with 3 variables. So I'm going to have y equals beta 0 plus beta 1, x1 plus, I'm going to leave out the i's. I guess I should add that though. Beta 2, x2 plus beta 3, x3. And I want my y to be murder rates. Murder rate in different countries. So I have that data. I also have age of first marriage. I also have population density. And I also have, I think it's median age. So let's imagine this is the setup that you're using for your paper. I purposely use this setup because I'm not really sure why age of first marriage would impact murder rates. And I'm not really sure why median, we can tell a story for median age, like maybe the older the population, the less likely they are to commit murder because murder tends to be, crime tends to be done by younger people. I can probably do population density, right? Like denser areas or denser countries are harder, easier to escape, because you can blend in with the crowd. There's more people to murder. There's more people to do the murdering. You can tell something like that. Largely, though, it's that being able to escape, right? I would say it's being able to escape. Easier to find people, too. So maybe I want to see what that matters. Now, the first step to do this in Excel is that when we did it before, we essentially drew a box that highlighted 2 columns. In other words, Excel requires, and to my knowledge, they haven't fixed this yet, Excel requires that all of your independent variables are next to each other so that you can draw one box to cover them all. It's really annoying. But we're going to have to deal with that. So I see age of first marriage in column H. I see population density in column I. I don't see median age. Where is median age? AJ. There you are. Thank you. So we are going to select column AJ and cut. Because we want to move it next to the other ones. So I'm going to right-click J and insert cut cells. And by whatever you select, it will insert it to the left. Now they're all next to each other. Age of first marriage, population density, median age. Oh, and nicely that matches up here with our beta 1, beta 2, beta 3. Are we good? Am I feeling the love? You want me to zoom in? Before giving these like loves. Okay. So data analysis, regression. We want to delete all of the old stuff because it remembers what we were doing before on housing data. We don't want that here. So, oh yes, it was AJ is where the median age is, and if you right-click it and cut, and then right-click J and you insert cut cells. Okay. Did you copy over? Did you copy over population density? Yep, there it is. So you want to right-click J and insert cut cells. There it is. Oh, perfect. And make sure to do insert cut cells. If you just, paste it, then you'll overwrite whatever you want to do. Then you overwrite something else, it will do that. Is everyone good? Okay, so let's highlight K1 through K237. And let's highlight H1, to J237. Again, I'm making that box so we get 3 variables. For our output range, let's throw it actually down to 250. Well, I can just scoot over some. One of the places. Let's do A250. Yeah. So I know where it is. This is how my setup. Does anyone have any questions? Yes.
I'm sorry, I missed it. You did the
Oh, now I'm doing 3. And all I did was I highlighted H1, or I typed in essentially. You can type in H1 colon J237. Because J237 is all the way down here in the lower right. H1 is right here, and so thus you made a box of 3 variables.
How about the first one?
With the first one, I just did K1, because you can only have one Y. K1 to K237. What's the question? Okay. So, yes. You cannot find the analysis. Sun under. You do it file first marriage. And you do the last stuff. As. That's like when you do it, so like always to take that off. Yep. That's great. Somebody can scroll the right side. So you can just go on it. No. That's so strange. Oh, wait. Well, yeah. No, that's just listening to the mind. Yeah, try to maybe reloading it or something. I'm not sure what's going on there. All right. Most of you are on the same page? Yeah. What's up, Anisha? Oh, yeah. Did you get an error? Yeah. You should have gotten this error. Did everyone get this error? Yes. Welcome to annoying thing about Excel number 2. And this one's particularly annoying. Excel cannot handle blank observations. Take a look at age of first marriage, Caribbean. We have no idea what the age of first marriage, Caribbean is. Excel sees blank data and I don't know what to do. Now, programs that are dedicated to regression analysis would automatically exclude Caribbean because we don't have the data. So we can't include in our analysis. And they would exclude Cayman Islands. And they would exclude Channel Islands. And they would exclude, all these other things that we don't need. Excel is dumb. It doesn't know that it should do that. So we have to do it for Excel. This is particularly irritating, but this is something that we have to do. So hit OK. Just to get out of that. You cancel. And we're going to go to our friend. Do me a favor, select everything. So if you select that triangle in the upper left-hand corner, you select the whole thing. So, we selected the whole thing, and go into sort. This is a really great function in Excel. I love sort. Because sort allows you to immediately find the largest or the smallest thing and then the order, or it can put it in alphabetical order for you. And it's really fast. The thing to remember about sort is you have to highlight everything you want sorted. So if I only highlighted population and I sorted it by population, then nothing would match anymore. So you have to be really careful. That's why I told you to select everything to make sure that you captured everything. The nice thing about sort for us fixing this problem is it will put all of the blank observations together in the same place.
Where did you go?
I selected everything and under data you hit sort. That's not everything, yeah. Oh yeah, you want to include labels. It's nice. If you semi-daters don't have headers, one, it will treat these as observations. You don't want that. Like population density is an observation, it's a title. And two, by making it as headers, it turns the first row into titles that you can easily see. So you can very easily find median age or age of first marriage.
And sort by.
Let's do age of first marriage. Let's start with the first one. Smallest to largest. Doesn't really matter. And when we do that,
Age of first marriage is male, correct?
it just says age of, I guess age of first marriage female. I don't think that's yeah. And when you scroll down, you can see, oh, it looks like Morocco, Taiwan, 27.8. In the 30s, age of first marriage, up. And then we stop at American Samoa. We don't have data for all these other observations. I'll skip the other. So I'm going to right click and insert. You can either delete those observations because you can't work with them. I'm just going to insert a space to remind me that I shouldn't use anything below that space. Here's the annoying part. I now have to do it with my other three variables, with my two other independent ones and my other dependent one. So, click, 175, oh, sorry. 175 all the way back up to the top. Sort, and then we do it for population density. And it looks like I don't know Taiwan's population density. So I'll select Taiwan, do it again, I'll also do an observation, and I gotta do it again. So this is a bit irritating, admittedly, but I do not know any faster way to do it. Monaco doesn't have any information on median age. Select the whole thing again, so I go all the way up. Sort and murder. So by murder, and you see all my murder is right here. Looks like I don't have murder rates for the West Bank and Gaza, the French Polynesian, Guam, New Caledonia, and Netherlands entities. And that leaves me with 167 observations. I'm on row 168, or one, the first row was dedicated to labels. Did everyone get to this part? No? Did I do it too fast?
Yeah.
Okay. No problem. I'm just going to hit Control 0 a lot. Did everyone get to this part? So I've sorted American, Samoa, and down. Okay, so you've been able to separate out, right? So you eliminated everyone that has blank age of first marriage information. Right. You got that part. So that means I can't use any of these observations because I don't have data for it. So I want to make a separation between the data I can use and the data I cannot use. So I'm going to right-click 176 and say Insert. That's a visual cue for me to know that I should only care about this stuff enough. Then I'm going to select 175 and drag all the way up. I don't want to highlight everything because then I'll be highlighting things I don't want to include. I'm going to drag 175 and up and go all the way up to 1, and it's sorted by the next variable. 175 and up.
Sort. Population density per square kilometer. And it looks like I don't include Taiwan. Right. Oh, Taiwan has a no into that. Taiwan will be excluded a lot anyway. Insert. So now I have a new barrier. Right, and now I only care about 174 now. And you just keep doing it for all your variables.
So a quick question.
Yeah.
So when you go into the regression, you don't have to highlight everything. You can just do 168. You can just delete 237 from 168.
Yeah, you can delete all the stuff you don't use now. That's sometimes I don't recommend you do that because if it turns out, maybe you discover your regression is dumb for whatever reason, or actually something we'll be talking about, especially next class. If you don't like your material, then you still have the data that if you want to change a variable, you can just resort it. So deleting it, you have to reload the whole, you have to, pull it up again. And then we do murder. And West Bank and God like that. So we should have 167 observations. Is everyone good? Again, it's really annoying. Yeah. Question. Where are you lost? The sort? So when you select everything, you can sort it. It doesn't matter if you do smallest to largest to smallest. The point is to put all the blank observations in the same place, for all the observations that have blank values for that data, or for that variable, I mean. And that way you can set them aside and then focus on the ones above it that you have, and then you just have to do that with every variable. You cannot, in case you're curious, you cannot do a thing when you add a level because it lets you sort, and then everything that's similar lets you sort again. So if you sort by location, and then if I had a continent variable, you can have it sort by continent, and then within each continent have a section. You can't do that here because, you might have an Asia first marriage at 22, and this might be blank, so then this would not be set aside, even though you should include it, right? You have to do this one at a time for every single variable, including your dependent variable. Does that make sense? You should have 167. It should go down to row 168 because you should have one set aside for the label. So you should have 167 observations. This is the stuff you have to throw away and ignore. This is the stuff you care about. When you give me summary statistics, this is the data you should use. When you give me the correlation coefficients, this is the data you should use. When you run the regression, because when you run the regression, that's the data that you use. So this stuff, down here, doesn't matter. This is the stuff that matters. Now, we can do the analysis. Regression, and the only thing I have to change is rather than going down to 237, I go down to 168. And 168. And I don't think I put the output low enough and it's rounding up. So I put the output starting all the way down to 250. I still have lots of space, so it's not going to be an issue. I won't override anything in case I care about that. All right. Is everyone good? Now do this. Will you run it? Oh, look at that. No errors at all. That was great. Yeah. So. Okay. You have an input wiring variables.
Most of my it's supposed to be only one, right? Because you only have one variable, so you only want to do the murder rate for y. You have 3 variables for x, 3 different x variables, but only one y variable. Well, move this out of the way so we can see. So you see k is the only one you have, so you only want to do k. So you want to do k1 to k168.
Yeah. What's up?
So you want to sort by, you first want to sort by age of first marriage. And then, okay, fine. And then scroll all the way down and see when age of first marriage disappears. And scroll back up. Yep, there it is, right there. Where is the law? And you right click 176 and then insert. And then you do that again for the variables. Well, I see. Scroll up. See that? Where is? I don't see median age. Median age of age that we face this whole year. Yes. Yeah, well, it's somebody that's going to overwrite themselves. Oh, wait, okay. Yeah, okay. And it's that theory that says that you have 9 observations. You might have missed something. Scroll up. Like all this, the only individuals, you have to do the sort for a one. I'm not sure why you're including agricultural land.
All right. So note, in the interest of time, we should move forward. Note that the only thing that's statistically significant is median age. And as predicted, if you have older populations, you have less crime because it's negative. The other ones actually don't matter. Interestingly enough, population density does not seem to impact crime, at least according to this regression. You could argue that maybe we just lack the right controls, like we did with when we did the housing data. We just don't have the controls put in. But maybe it actually doesn't matter. If we were to write our paper, and when you write your paper, you pick one variable you find to be particularly important. If we were to write a paper and we chose population density, that's what's really important to reduce crime. And then we found this when we ran the analysis. This does not mean we did something wrong. It means we found evidence that our initial assumption was incorrect. That's not a bad thing. That means we have to change our thesis statement. And turns out we have evidence that says it's not actually true. You might think it's true, we might say in our paper, but it's not true, and then we come up with some good reasons as to why it wouldn't be true. Some countervailing effects that explains why it's not true. Do not do the thing that I've seen people do over and over, where they have their thesis, right, from the proposal, and they just use it again, even though their data completely contradicts it. They will say, oh, population density is so very important to predicting murder rates, and then they give me data that says it's not. Well, don't do that. Don't be that person. Yeah.
It's up to you. So, for one, in your paper, you will select one that is your focus, and the others will be controls. So, if your controls are statistically significant, who cares? Because that wasn't the focus of your paper. If the focus of your paper isn't statistically significant, either pick a new variable or go with it and say, look, everyone thinks population density should impact murder rates. It doesn't, right? You use that story and say, no, and then come up with some reason for some other effect that would cancel it out. Like, because population density also means there's more police or something like that. Yeah.
since the proposal is kind of a first draft, can we still change our independent variable?
Absolutely. Yeah, absolutely. It was just to get you started. Any other questions? Yeah.
So we do this homework, so the table, are we supposed to use data set 6?
No, you use memo data set. This is just, data set 6 is part of memo data set, but it's just a short version of it. Just so we can get used to working with it. Alright, I need to go over some of these other parts. And then I'm gonna let you go.
So before we talked about residual sum of squares, which is right here. But we also have this, which is regression sum of squares. This is essentially the amount that we can explain. We call it explained sum of squares, or the sum of squares due to regression. Mathematically, it is equal to, just like before, the sum, I equals 1, n, and then, but now it's a little something different.
Now, rather than taking the difference between what we predict and what we observe, we take the difference between what we predict
And the average. I was actually putting my eyes.
It's essentially saying if you didn't know anything about a country, if you know anything about a house, we'll say you would expect the house's prices to be the average price. If you know a bit about its size and location, then you can predict a certain amount. And that difference between what you can predict and the average is what you can explain. If you take the residual sum of squares and add it to the explained sum of squares, you would get the total sum of squares.
So what are we doing?
We are discussing these various parts in this output. Here's the total sum of squares. It's the sum of these two. This leads us to two ways to evaluate the model as a whole. Before, all we get to do is evaluate the individual components. If that's statistically significant, that's not. But how's the model in general? Is the model in general a good model or a bad model? Does it explain a lot or a little? One way to do that is with the F-stat. A significant F that's associated with it works just like p-values. In other words, this is a very small value right here. You know, a point, and then there's like 10 zeros, and then 3 1. So that's very, very small. F-stat's really large. So it's pretty good. Some of the ratio between the residual and the explained.
So the significant F is larger. It's like looks like a little bit better.
Yeah, exactly. Yeah. So that's kind of nice. We have the standard as to what it means, but we don't have a lot of great intuition. It gets into a lot of what's called analysis of variance. That's what ANOVA stands for. We're not going to get into that in this course, but it's one measure to evaluate how good it is. The other way to measure how good it is to look at something that's a bit more intuitive, and that's R squared. R squared is the ratio between the explained sum of squares and the total sum of squares. It is essentially how much of that variation you are explaining. You know, murder rates are up and down for all kinds of reasons. We're explaining about 27% of that variation. The problem with R squared is that there is no standard of what's a good R squared. There's no standard what's a good R squared. I need the board space. In my like 5 minutes left. It's 27%. Is that good? Is that bad? I don't know. No, the other one for the housing I think was in 33% or 0.33, something like that. Is that good? Is that bad? I don't know. It seems fine. Yeah, it was what was it? Yeah, 36%.
So that's like saying basically how close your regression line is.
Mm-hmm. Yeah, essentially. You can think of it that way. Yeah, because everything that's left over is residual. So the smaller the residuals, the closer everything is to the regression line.
So what we need to know then for the table and or
Yeah.
we have to do this for the table?
Yep. Yep. And you'll see that in the sample. The other problem with R squared there's this problem with no standard, but F-stat kind of does a good job, right? Because it has these significant levels built in. But R squared also has an additional problem, is that adding explanatory variables always increases R squared, even if those explanatory variables do nothing. If I were to run that regression again and I were to exclude population density, I would get a lower R squared, even though population density didn't add anything. It wasn't statistically significant. Always. That's why we have another stat you can see just below R squared on your printout, adjusted R squared. And that penalizes you for explanatory variables. It is equal to 1 minus R squared and minus 1 and minus k minus 1. Where n is the number of observations, and k is the number of explanatory variables. Just to be clear, we're not including the intercept. Note that as n increases, all things being equal, there's a smaller and smaller distinction between R squared and adjusted R squared. If n was, say, 4, then this ratio would be kind of large. It would be pretty big. If n was, say, 100 and k was, I don't know, like 3, then it would be very similar. It would be 99 divided by like 95. It's basically 1. Or 96, I guess. 99 divided by 96. So it again highlights the importance of having lots of observations. It also tells us that our explanatory power, the number of variables we can throw into the regression, is limited by our number of observations. If we have 5 observations and 4 explanatory variables, we basically know nothing. It's just a mess. Don't do that. It's kind of like saying, I'm going to predict your income 10 years from now, and I'm going to use as many variables as there are people in the classroom. Which means, Adam, I'm going to explain your income 10 years from now because you're wearing that gray shirt, and no one else is wearing that kind of gray shirt.
And Michael, your income is because of that jean jacket. Right, and no one else is. And Ike, your income is because of your haircut. And no one else has your exact haircut. Right, that's stupid. That doesn't make any sense. But it would come out as being completely predicted because everyone would just have a unique variable just for them. Right. So keep that in mind. All right, with that, on that note, I'm going to let you go. Want to talk about W variables again? Didn't have time, so we'll talk about those on Thursday. Have a great couple of days, everyone.